Hey everyone, and welcome. Today, we're going to break down the system design of a platform that, let's be honest, many of us spend a lot of time on. A coding interview site, something just like LeetCode. So, let's just jump right into the big question. How in the world would you build a website that can safely run code from, say, 100,000 strangers all at the same time? This isn't just about making a web page look pretty, it's about building a powerful, secure engine that can handle a massive scale. So for this explainer, we're going to put on our engineering hats. We're going to approach this just like we would in a real system design interview, starting from a completely blank page and working our way to a full design. And that means starting with the most important step of all, figuring out what exactly we're trying to build.
All right, let's get into it. The first thing we need is a blueprint. And a good blueprint means mapping out our requirements by splitting them into two groups. What does the system do, and how well does it need to do it?
So on one side, you've got your functional requirements. These are the core features, the things you can see and click. Viewing problems, submitting your code, getting that instant feedback, and seeing a live leaderboard. But on the other side, and this is just as important, are the non-functional requirements. This is all about quality. The site needs to be up and running all the time, it has to run code securely, results need to pop up in under 5 seconds, and it has to handle 100,000 concurrent users without breaking a sweat.
Okay, with our goals locked in, let's start laying the foundation. What are the fundamental building blocks of our system? What information do we actually have to store and manage?
Well, first up, the problem itself. We obviously need a data structure, or an entity, to hold everything about a specific problem, its description, all the hidden test cases, and of course, what the correct output should be.
Next, every single time a user smashes that submit button, we need to track it. So we need another data entity for the submission, which holds the user's code, what language it's in, and ultimately the result, pass or fail.
And finally, for the competitive side of things, we need a leaderboard entity. This is what's going to store and manage the rankings during a live competition.
Now, these three pieces of data are basically served up through 4 simple API endpoints. You can think of these like the digital doorways to our system. They let users get a list of problems, dive into a specific one, submit their solution, and check the leaderboard. That's it. It covers all our core features.
All right, now that we have our data models and our APIs planned out, let's put together our first, very simple version of the system. We're going to start small and just focus on the basics, letting a user read and display problems.
For just showing problems, the design is super straightforward. Your web browser, that's the client, asks our API server for a problem. The API server then grabs that problem's data from a database. And here, a NoSQL database is a great choice. Why? Because each problem is its own self-contained package of information, so we don't need a complex web of tables. It's flexible and scales really well.
But let's be real, just displaying text is easy. The real magic and the absolute heart of this whole design challenge happens the moment a user hits that submit button. This is where things get interesting.
We've now arrived at the hardest part of this whole system. How do we take code from thousands of strangers and run it safely, quickly, and efficiently without, letting someone blow up our servers?
So this brings us to a really important concept in the industry called the long-running tasks pattern. See, running code can take a few seconds, and in the world of the web, that's basically an eternity. You can't just freeze the user's screen while you wait. So the idea is the API responds instantly with something like, "Got it, I'm working on it," while the actual heavy lifting happens in the background.
So how do we actually do that background work safely? We use containers. The best way to think about a container is like a secure, totally disposable little workshop that we spin up just to run one piece of code. It's completely isolated, which means if the code is buggy or even malicious, it can't mess with our main servers or anyone else. Now this is where we build our digital fortress around that code. To really lock that container down, we do a few things. First, we make the file system read-only. No deleting or changing critical files. We put strict caps on how much CPU and memory it can use to stop it from hogging resources. We set a hard timeout, say 5 seconds, to automatically kill any infinite loops. We completely block its access to the network so it can't phone home to some malicious server. And finally, we use something called setcomp to severely limit which system calls it can make, basically cutting off its access to the core of the operating system.
Okay, we've solved secure code execution. That's huge. But now, let's level up the design. It's time to make this system tough enough to handle the insane pressure of a live competition with 100,000 users all banging on it at once.
So, for our leaderboard, the simple, naive idea would be to just ask our main database for the new rankings every few seconds. But can you imagine what happens when you have thousands and thousands of people all doing that at the exact same time? Yeah, you'd completely crush the database. It would grind to a halt.
And this is a classic case of using the right tool for the job. Instead of hammering our main database, we offload all that leaderboard work to an in-memory cache, like Redis. It's literally built for this exact scenario. Super fast reads and writes, all happening in memory. This keeps the leaderboard feeling instantaneous and takes all that pressure off our core database.
And what about those huge traffic spikes? You know, the last minute of a competition when everyone submits their code at once? For that, we introduce a message queue. You can think of it like a buffer. The API server just throws all the submissions into this queue, which then feeds them to our execution containers at a nice, steady pace. This means we never lose a submission and our system doesn't get overwhelmed.
So, after all that, let's take a step back and look at our final, robust, competition-ready system architecture. It's ready for prime time.
Look how far we've come. We went from a simple client and server to this really sophisticated, scalable system. We've got specialized components for every job, a database for storing our problems, Redis for that lightning-fast leaderboard, a queue for resilience, and a fleet of secure containers to safely execute all the code. So, really, the main takeaway here isn't just how to build a coding platform. It's about these timeless principles of good design. You start simple, and then you layer on complexity. You always use the right tool for the right job. You actively look for and solve bottlenecks before they become disastrous. You don't over-engineer things, and most importantly, you always put security first. These rules apply to pretty much anything you'll ever build.
This whole process, breaking down a really complex problem into smaller, solvable pieces, that's the soul of engineering. And it kind of leaves you with one last question to chew on. What other apps that you use every single day are hiding this kind of complex architecture, solving even bigger challenges right there in the palm of your hand?